Thank you very much, and apologies once again for all that. It's a pleasure to give this talk, and thank you also for the organizers. Hopefully, I mean, this is a very non-trivial organizational problem. Hopefully, in the next version, we will all meet in person over there. So my title is Black Holes in String Theory and Modular Forms. And now both these subjects, black holes and modular forms, are important subjects in their own right in physics and mathematics respectively. And what I want to do today is to describe some connections, surprising connections between these fields, which have arisen in a class, in the study of a class of black holes, namely supersymmetric black holes in string theory. And following the advice of the organizers, namely that the audience is very diverse but shares the common language of mathematics, I'll discuss some elements of both these subjects, black holes and modular forms, very briefly, that allow me to just describe these connections that I referred to, and that will essentially take up all my time. So my goal will be really to just communicate the broad ideas, and if you want to know more details, feel free to message me or email me. Yeah, please don't use fancy ways, just email is good. As you see, I'm not very good technologically. Okay. Also, apologies to, well, the string theorists, because you probably know everything that I'll say. There'll be no new material, only maybe towards the very end, I'll mention some work, current work. On the other hand, I mean, this is really supposed to be for non-experts, so please feel free to interrupt with any question or comment during the talk. That will really, really help me. Of course, also later. Okay, so then let me begin. I'll start by telling you a little bit about modular forms, a little bit about black holes, and then what the connections. Okay, so let me start with modular forms, and now I want to go here. So stop sharing. Stop sharing. And start here. Share. Okay, I hope you're seeing that, and I hope you're seeing that. Yeah, perfect. Okay, so let me just start with a very brief introduction to modular forms. So let's start with the upper half plane. So the space of complex numbers with imaginary part positive. Okay, that's that. And SL2Z, the space of, so the set of the group of integer matrices with unit determinant, 2 cross 2 matrices with unit determinant, has a natural action on the upper half plane as follows. It takes any point tau to a tau plus b over c tau plus d. These are fractional linear transformations. And I'll give you sort of a working definition of modular forms. There are more sophisticated geometric ways of understanding it. But today we just need the following. So it's a class of functions I'll talk about today. So these are holomorphic modular forms. The holomorphic functions on the upper half plane, which essentially, for which this is a symmetry in the following sense, that f of a tau plus b over c tau plus d equals f of tau times c tau plus d to the power k, where k is some integer called the weight of the modular form. Okay, this should be true for all elements in SL2Z. Okay, so that's called a modular form. If k is 0, then you see that f is really a function which is invariant under action of the modular group. This is called the modular group. That's a bit too restrictive, but when you allow for this kind of k, those are called modular forms, and that gives a nice, interesting class of functions. This k with this definition should be an integer, but in fact there's a slightly more detailed definition which allows for half integers, which we'll use. I won't give you the definition. There are some numerical factors here. Similarly, the definition can be extended not beyond SL2Z to discrete subgroups of SL2R. Okay, I won't give you the definition, but essentially this is at the heart of it. Okay, there's some numbers there. Now, if you look at A, B, C, D equals 0, minus 1, 1, 0, you see that f of minus 1 over tau is tau to the k times f of tau. So you immediately see that so the function here is related to the function over there. And you can begin to appreciate that this is a very restrictive symmetry. And there's an infinite number of such relations. Okay. In fact, this symmetry is so restrictive that the space of modular forms with a given weight k is actually finite dimensional. Okay, so there's this very, very few functions which obey this property. Okay, the fact that this is finite dimensional, you'll see how powerful it is in a second or in a minute. But now let's look at another consequence. If you take A, B, C, D to be 1, 1, 0, 1, then you see that f is actually a periodic function, period 1. That means it has a Fourier expansion. Okay, so a n q to the n, q is e to the 2 pi r tau, a n are some numbers. And this n here, oops, should be an integer. But because you want f to be holomorphic, notice that tau goes to infinity, I infinity means q goes to 0. If you want it to be holomorphic everywhere at q equals 0 as well, then n should be greater than equal to 0. In fact, in physics, we want to slightly weaken this condition. What we'll do is allow for a small exponential growth where n0 is some fixed number. So that's so this is called weakly holomorphic modular forms, and this is often the case in physics. Okay, so you can develop the theory of this as well. Okay, now let's look at this equation. So what this is saying is that this function f of tau can equivalently be thought of as this sequence of numbers, a1, a2, or maybe a minus 1, etc., with some set of numbers, semi-infinite. Okay, and often in many cases in mathematics and physics, this is how modular forms make their appearance. I mean, unless you go to study the theory of modular forms, you're studying some other problem and you find you have a mathematical problem which is labeled by the integers, whose answer is a number. You make that sequence of numbers and you find that they happen to be the coefficients of a modular form. Okay, so that kind of a surprise happens again and again in many, many places in mathematics and also physics. So that's how they sort of make their appearance. So here's an example from number theory. So take an to be 1 if n is a square and 0 if n is not a square. Okay, so that modular form is just you take the sum over all integers q to the n square. That's called the function theta. This is a function which has been studied for more than 100 years, 150 years, called the theta function. That happens to be the modular form of weight half under some congruent sum. Here's another example. So take this slightly more sophisticated, take this function. It's also a series of the type that I showed you. So it's coefficients of q to the n, where the coefficient r2 of n is given by the sum over the odd divisors of n of -1 to the d minus 1 over 2. Okay, it's a simple definition. Turns out you can show that this is also a modular form of weight 1 under some certain congruence subgroup. Now, the fact that theta has weight half means that theta square has weight 1, and it turns out that they transform under the same group. And if you remember, I said that these spaces are finite dimensional. It turns out that that space is actually one-dimensional. So in fact, they must be equal up to some constant, and I've sort of shown you the constant over here. I mean, this is rigged up such that the constant is also correct. Okay, so you see immediately the power of modular forms. What this is saying is, on this side, what you have, the coefficient of q, is the number of ways that an integer n can be written as the sum of two squares, because each of them is a square. And on this side, you have an explicit formula. Okay, so you immediately get this formula for the number of ways an integer can be written in terms of two squares. Okay, I mean, this formula is more elementary. You don't need this to prove it, but this just to show that if you want to show equalities of functions of this type, if you know that the left-hand side and right-hand side are both modular forms transforming in the same group, because the space is finite dimensional, you just have to check one or two or some finite number of coefficients, then you have a proof for all n. Okay, so that just to give you some indication of the power. I'll stop this, go back to my slides. I've lost it now. Here it is. Okay, so let me continue. Can you see this? Yeah. Okay, so that's all. All this I said. So you have a sequence of number. Here I gave you one example. So here's another example, which many of you might have seen. If you ask what is the generating function of the partition problem, partition an integer into smaller integers, it's the following: you strip off this prefactor, you take the inverse, and that's exactly the generating function. Okay. So you see that. So I gave you one example from number theory, one from combinatorics. Similarly, there are, the same thing happens in other subjects, topology, geometry, in many places in mathematics, and also in physics. Okay. All right. So that was my very, very brief review of modular forms that we need. I'll now move to black holes unless there are questions. Okay. I can go to the screen. So what are black holes? Black holes are physical objects. They're up there in the sky. They're regions of space-time which are surrounded by one-way surfaces called event horizons, which means things can fall in, light and other signals and matter can fall in, but nothing can come out. And they're formed typically by the end product of the collapse of very heavy stars, very massive stars. Now, at the end of the collapse, you have some black hole, and I mean, this is a subject which is studied a lot by astrophysicists. But from the most theoretical point of view, at the end of the day, when things are static, these objects can be described as solutions to Einstein's equations, classical general relativity, with no matter. And then you can ask the following question: suppose you have some object of mass m and length scale L. When is it a black hole and when it's not a black hole? Imagine this is a star. And the criteria is very simple. Let me describe situations with spherical symmetry to make my life easier. Criteria is simple. You just calculate this number called the Schwarzschild radius. It's 2 times the mass times the Newton's constant. That has units of length. And if this Schwarzschild radius is smaller than L, the typical length scale, then you don't have a black hole. So this is a star. I've just shown you some Schwarzschild radius over here. This is what the Earth or the Sun or we look like. But if our Schwarzschild is bigger than m, then what you have is something like this. You have a black hole solution. Outside is vacuum, and you don't know what went inside. Okay, I tried to show this with a picture. Everything is black. No signal can come out. And this is the solution. So the way to say this is that you have a solution of general relativity. And the solution is a very smooth, featureless object. It has no information about what went in, characterized completely by its conserved charges. In this case, the mass. But when you have electric charge or angular momentum, there's also those. Okay. So that's the picture in classical general relativity. It's sort of a cold, simple object. In the quantum theory, the picture is completely different. The black hole is supposed to be it's like a hot piece of coal. It's a very complicated object with lots of degrees of freedom. Okay. Now, this was discovered by Bekenstein Hawking in the 1970s. The combination of a very profound argument and a beautiful calculation. And the argument is actually very simple. I can't even say this now due to Bekenstein. It's simply the following. Take some object with entropy, throw it into the black hole, and what happens? Okay, so any object has energy and entropy. So the black holes have divided the universe into outside and inside. So you lose energy from the outside world, but correspondingly, you can show from Einstein's equations that the mass of the black hole also increases exactly correspondingly. So the first law of thermodynamics, that's the conservation of energy, is completely fine. But it would seem that you would lose entropy from the outside world, thus violating the second law of thermodynamics, unless you assign an intrinsic entropy to the black hole itself. Okay, so this sounds like a very simple argument, but it's a very profound one, and it took years to make it, and a lot of daring to make this argument turned out to be correct. And then a couple of years later, Hawking had this beautiful calculation. So if the black hole has entropy and mass, then it must also have temperature because of the first law. So how do we calculate this temperature? Okay, so this is a very deep calculation, whose answer. So this is not very easy to describe, but the answer is easy. Here's the formula for the temperature. Okay, this is derived using a combination of quantum field theory and general relativity. Okay, now I can put these two together, and this is the first law of thermodynamics. You know the mass, you know the temperature. So you can integrate this to calculate the entropy, and this leads you to the famous Bekenstein-Hawking entropy formula. It says that the entropy of a black hole is a quarter of the area of the event horizon of the black hole in Planck units. Okay, so a very beautiful formula, including all three fundamental constants of nature. You don't have many such simple formulas. Okay, so that's the entropy. Excuse me. So you can ask, well, so what? So what if a black hole is entropy? Well, in fact, it's a very profound statement, because the way we understand entropy in the rest of physics is from the idea of Boltzmann, that the entropy measures how many degrees of freedom there are in the system. So the Boltzmann formula says that the entropy should be the Boltzmann constant times the logarithm of the number of microscopic states of the system. Now, if you combine this with the black hole entropy formula, it tells you that this black hole entropy must be equal to the logarithm of some number of microscopic states, which you can associate to the black hole. Of course, it's not exactly right, because Boltzmann's formula only holds in the thermodynamic limit. The size of the system becomes very large. That's what I've shown here by these dots. And in fact, that's an important thing. If you know what this number of microstates of a black hole is, and if you can calculate these deviations from the thermodynamic limit, that gives you information about deviations from general relativity, because this is the universal formula in classical general relativity. So this is some sort of window into quantum gravity. It's a whole story. I don't want to get into it here. All right. So this sort of finishes my review of black holes and black hole entropy. And the sort of bottom line is simply that given any black hole, you can associate an integer called the number of microscopic states, at least approximately, to the black hole. Okay, now we'll move to string theory, where this can be made more precise. Okay, any questions? All right. So in string theory, one has two pictures of a black hole. One is the usual one that I just showed you as a solution to Einstein's equation, and here is some set of conserved charges of the system. But remember, I told you how when to say when a black hole is formed or not. The criterion involves the Newton's constant, and in a class of supersymmetric vacuum and string theory, Newton's constant is governed by what is called the string coupling. And in a class of supersymmetric situation, the string coupling is a free parameter. You can tune it. And so when that becomes large, the Schwarzschild radius is large, you have a black hole. And when it becomes small compared to the characteristic scale of the fundamental objects of string theory, you have a completely different picture. Namely, you have an ensemble of microstates. So when the Schwarzschild radius on the left is smaller than the Compton wavelength of strings, that's the criteria. Okay. So you have these two pictures. The quantum numbers n are same on the same side, and because of supersymmetry, we expect that the number of states appropriately defined is the same. And therefore, you can just calculate the statistical entropy, the Boltzmann entropy, using this ensemble. And this is what was pioneered by Strominger-Waffer and Sen. And they found that indeed, they did one example where they showed that they calculated the statistical entropy and showed that that's equal to the thermodynamic entropy. Okay, so it's a big breakthrough of string theory. It explains the statistical origin of thermodynamic entropy of black holes. Okay, it tells you what the molecules that make up the black hole are. I just showed you one example here, which came soon after Strominger-Waffer, where the black hole is actually labeled by one integer called n, and the area is 4 pi times square root of n. And what you have to do is to calculate the number of states in this ensemble, and then you have to estimate how many states there are as n goes to infinity. That's the thermodynamic limit, and you find indeed e to the pi square root of n. Okay, so now what I want to tell you next is, again, there's many things to talk about, but I want to focus on how you get such estimates. So given such an ensemble, how do you get such an analytic form? Okay. Now, in order to do that, you need to know exactly what this ensemble is. And for this example, which is the simplest example, type 2 strings on a Calabi on a T6, the answer is that it's some D-brane configuration. So generally speaking, when you have such a configuration, these objects are fundamental objects of string theories, branes and strings and so on. And typically you can realize them as some D-branes of various types wrapping cycles of the compactification manifold. Recall that string theory is 10-dimensional. The black holes we're talking about is 4-dimensional. So there's some Calabi-Yau compactification. Calabi-Yau has some cycles, and you have D branes wrapping these cycles. Okay, so in this simplest situation, you just have a T6. And instead of thinking about complicated D branes, let's just talk about, so the point is that these are extended objects. So let's talk about the simplest extended object, namely a string. Okay, just to get a feel for the problem. And you have a string wrapping a circle, you can ask, what is the entropy of the string? Okay, so you have to ask what are the modes of excitation of the string. And this is a very simple problem. You solve the Laplace equation, and you have some oscillators. This is 1 oscillator, 2 oscillator, 3 oscillators, etc. And the problem now becomes, given some energy, how many ways can I put that energy on the string? In other words, divide that energy into these various oscillators. Okay, each oscillator has energy. Now, this problem is the same problem as asking how many ways can an integer n can be partitioned into smaller integers. So let's just run through it. So actually, I think all of you have seen this, but it's a fun problem. So you take 1, there's only one way of writing it as an integer. So P of 1 is 1, P of 2 is 2, P of 3 is 3. And this is a lesson for physicists that you shouldn't stop after a few examples. The answer for P of 4 is not 4, but it's 5. But in fact, as I think all of you know, this function actually exponentially increases. P of 10 is 42, P of 200 is this big number. Okay. How do you solve this problem? You calculate a generating function. So each of these are oscillators. So for the first oscillator, you just allow it to be whatever excited as many times as it wants. So 1, q, q squared, etc. The generating function is 1 over 1 minus q. That's the oscillator with energy 2, 3, etc. Combine all of them, and you get this function, which is precisely up to this prefactor, the 1 over the Dedekind eta function. Okay, so you begin to see the appearance of modular forms in such problems. You could tweak the problem a little bit. Instead of bosonic oscillators, you can have a fermionic oscillator, in which case the energy is quantized in units of half, and you're not allowed as many excitations because of the Pauli exclusion principle. You only allowed one no oscillator or one oscillator. That gives you some theta function. Okay, so a lot of modular forms begin to appear this way. And if you go back to our problem, the result of this paper for the simplest examples can be phrased as saying that there are effectively 5 bosonic directions and 2 fermionic directions. And the answer, therefore, is some theta over eta to the 6. Okay, this eta is exactly the eta I showed you. The theta is the theta I showed you in the beginning, except for some small dressing here. Okay. So now that you know what these functions are, you want to estimate it. And the claim is that you can estimate it very easily. And the answer is that e to the pi square root of n. Okay. So I want to now give you a feeling. So this was a small, this was to give you a feeling for why you get modular forms in the problem. Okay. Now I want to show you, if you have modular forms, so what does that buy you? Okay, so how do you calculate such things? Okay, again, it's a small sketch. I want to go back to my iPad, but it's logged me out. Join, leave and join. Sorry, I'll leave this. No audio. Share screen. Good, I'm getting better at this. Here we go. All right. So, oops, can you see it? No, I can't see it myself, so something wrong.
Not yet, no.
Yeah, it says it's sharing screen. I'll stop. It's because I'm not in the meeting. End meeting. So go back. I'll try and go back to the link. Perfect. Now I should be on.
Yes.
Okay. Here we are.
Yeah, very good.
All right. Okay, so where were we? Okay, so take a modular form of this type. Now I've called it f of q instead of f of tau. Right is Fourier coefficients. And you want to invert this formula. Okay, suppose f is some modular form. You want to invert this formula. You write a contour integral, okay, and pick up the nth coefficient. Now, in the Q plane, remember, where the upper half plane in tau maps to the unit disk, and typically, well, by what we said, these functions are actually holomorphic over here, except maybe at 0. So this contour integral you can deform. Let's take an example to be this partition problem, 1 over eta of tau. Turns out that it's holomorphic everywhere here, but on the unit disk, this function actually becomes singular. Okay? And the dominant singularity is at q equal to 1 or tau equal to 0. So to estimate this contour integral, you have to deform it, go very close to this point q equal to 1. Then the most of the contribution to this integral over the contour comes only from this piece of the contour. And over there, you can replace the function by an estimate of the function near the singularity. That estimate you can do very easily using the modular transformation, because f of tau is related to f of tau is related to f of minus 1 over tau. So 0 maps to infinity. At infinity, you can use the Fourier expansion. You immediately get some formula of this type. Okay, so you get an asymptotic formula of this type. And in fact, you might recognize the Bessel function here, but if not, you can even do a saddle point approximation and you get this exponential very easily. Okay, so that's how you get these kind of exponential formulas. But in fact, one can say a little more. If you think about this contour, the function has singularities not just over there, but in fact, at all roots of unity on the unit circle. They're all subdominant, but they're all exponentially growing. So in fact, what you have to do is to take a contour which sort of goes there and then goes near every rational point. That's a sort of tricky problem, but this has been solved by analytic number theorists. And if you have a modular form, you can actually calculate A of n exactly, and it's completely determined by some finite number of coefficients, okay, by these kind of methods. This is called the circle methods, which was developed by Hardy and Ramanujan and Rademacher. And now I want to go back there. This is the last time I'll flip-flop. Share screen again. Wow, I lost it. Here it is. Okay, so that's again a very brief idea of what the methods are. So in our case, you have some modular form of 8 minus 1/2. You can obtain, as I said, an analytic expression for this integral. It looks like this. Okay, you have some infinite sum over Bessel functions. You saw why there are Bessel functions. And this Kc is called a Klosterman sum. It's some sum over phases. This does not grow at all. I won't talk about this today. And if you remember your Bessel function, there's an I Bessel function. The leading asymptotic as the argument goes to infinity is e to the z. So you see that for c equal to 2 at 2, 3, 4, these are exponentially suppressed. So the leading term is just the leading Bessel function. And then you can further do an asymptotic expansion of this Bessel function. Just look up some book or some Wikipedia, and you get something like this. Okay. So this is the sense in which you get an exact formula, and this is an analytic formula. Okay, so that's the role of analytic number theory. And now we want to interpret this in physics. If you remember my slides, I'll do this here. This pi square root of n is exactly the Bacon-Stern-Hawking entropy. Now, if you believe in this whole picture of string theory, then, I mean, this is what Strominger and Waffer first did, and many people following that. But in fact, if this picture has to be correct, then not just is the leading estimate correct, but also the subleading terms. If really string theory is consistent, and you have this ensemble of microstates, and you can count in this case what these numbers are, then not just this, but you should, all these subleading corrections should also be accounted for from the physics of the black hole. And that's a very beautiful story which has been developed in the last 10 or 15 years. It turns out that this leading log correction comes from the calculation of a one loop calculation in Einstein's theory, and the leading log correction is actually unambiguously calculable. This was shown by Ashok Sen and collaborators in a series of papers. And similarly, the subleading power law terms can be calculated depending on your string theory model that was pioneered by Cardoso and Lewitt and Mohabd. And then it turns out that you can actually sum up all these perturbative calculations using some technique called localization, and you can actually get these Bessel function. And sometimes you can even get some non-perturbative effects. The point I want to make is that that this fact that this integer must have an interpretation in the black hole physics is a very stringent constraint on whatever theory of quantum gravity it is, and string theory seems to pass this in flying colors. Okay, so that was to show you that. So the title here was modular forms and black holes, to tell you what modular forms buys you for physics. But now in the last, I don't know how much time I have, Johan.
Sorry, I was unmuted. I was muted. Sorry. So you've. I thought that you still have 5 minutes if you can take them, and then you will have 5 minutes for questions.
Okay, so 5 minutes. So now I want to show you how the information can also go a little bit in the other direction, why mathematicians are interested. So I showed you how to each supersymmetric some integer called the microscopic number of states. And in this philosophy of modular forms that I first showed you, you can just ask, make the generating function and ask what kind of function is that? Does it have modular properties? In this one example, I showed you that it's the case. Now, quite surprisingly, it turns out, so it's not very easy to calculate these integers in all situations in string theory, but in all the cases that one can, it turns out that the answer has something to do with modular forms. Okay, sometimes you understand why, sometimes not, sometimes a surprise. Okay, so each case you clearly, when you find something like that, it's of great interest because we get all these techniques which we can use for physics. It's also of interest to mathematicians because you get new examples. One example is you do type 2 strings. Instead of T6, you do K3 times T2. Instead of modular forms, you get something called mock modular forms. More recently, you can think about black holes in ADS 5 times phi. Those seem to be related to something called quantum modular forms. This is a notion which is very new. Maybe I'll just sketch a little bit about this mock example. What are these mock modular forms? So modular forms are these holomorphic functions which behave nicely under the modular group. Mock means that, so these were functions discovered by Ramanujan 100 years ago in his last letter to Hardy, just before he passed away, where he wrote a list of 17 examples and said that, I'm very excited because I found something which are almost like modular forms, but they're not quite. We call them mock theta functions. Mock in the sense of fake. He didn't give unfortunately, he didn't give a definition. And then in the 80 years following, mathematicians developed many examples which felt like what those functions were what Ramanujan wanted to say. So the class of examples became larger. And then in the last 20 years, a theory has been developed due to work by Sanders Vegas and other number theorists. And now we have a theory, a definition. Essentially what it is you have a function which is not quite modular. You can add to it a very specific function. G is a function of a function called, G star is a function of G, which is called the shadow, such that the sum becomes modular. So f hat obeys the modular transformation property, but this thing that you add is not holomorphic, and therefore f hat obeys an equation of this type. The d tau bar of f hat equals some other function g bar. Okay, so this is like a holomorphic anomaly equation. But for physics, the point is that at the end of the day, after doing this, you get back the power of modularity, and you can sort of continue this program of trying to understand quantum gravity in the sense that I just described. But on the other hand, because for every black hole you get, you can associate a number. If you change the class of black holes, you get a new function. And in this case, for instance, for the K3 compactification, you just have to change the magnetic charge. For every magnetic charge 1, 2, 3 up to infinity, you get a new mock modular form. And that family, that infinite family of mock modular forms and the related family actually contains a lot of the examples which were discovered in the mathematical literature separately, and contains new examples. Okay, so this is one reason mathematicians are interested. I'll just stop. I'll end with it's a very sort of a small reference to something current, which is that recently it's a completely different type of black holes, but it's the same philosophy. You study these black holes, you associate these microstates, and you ask, does the generating function have any interesting property? And it turns out that for ADS5, supersymmetric black holes in ADS5 space, the generating function is very closely related to what is called a Kronecker Eisenstein series, which is again something studied for a long time by mathematicians, but in fact a particular case which was studied for 30 years or so intensively by number theorists. So this is called the Bloch-Wigner logarithm, and it's not the theory of these functions. Not the Bloch-Wigner logarithm, but the functions I'm talking about. It's not been developed completely, but it seems to be related to a notion which is very recent, which has been developed by Don Zagier, called quantum modular forms. And the idea is something very similar, that it's not quite a modular form, but it's close to a modular form in a sense that one can make precise. Okay, so I'll stop over there. I'll just leave you with this quote by Boltzmann, which I think is very appropriate for the present state of quantum gravity. Thank you very much.
Thanks, Amir, for a very nice talk and for covering a lot of ground in a very pedagogical way. Thanks. Are there questions for Samir, either in the chat or just unmute yourselves, please? No questions.
Can I?
Yeah, please. Yeah, please.
Sorry, this is more of a philosophical question for Samir. Because you've thought about this much more than I have. It seems like generating functions for partition types of problems tend to exhibit modular behavior, even though they live in two completely different worlds. Do you have a feeling why this is the case?
Let me think. Firstly, the statement is so. The interesting thing about that statement is that it's not quite true, as I think.
Okay,
you know.
Good. So okay, good.
So not all partition type problems give modular behavior. So in
fact,
that's
why I said tens.
Yeah, no. I see. No, I mean, I know that you've thought about it. So it's a very good comment to make that it may not be a modular form, but oftentimes you get something like a modular form. So that's what I think you meant. No, I don't have a feeling for why that's the case at all. I mean, technically, case by case or in some class of examples, one can think about it. But I mean, it's no. So I don't have anything to offer. But instead, I'll just sort of flesh out your comment with some examples. So the partition problem, indeed, we know that's the case. And that's one of the first examples of a modular form in such a context. If you now start changing the partition problem, you say, well, I want partitions of an integer, but only restricted to a certain size, something like this. Then you say that I'm only allowing a certain number of partitions where the maximum, the integer inside the partition can only be of a larger size, or the number of parts can only be of a certain size. You can refine the problem in many ways, and then you can start putting. Typically, those problems also are modular. But now you can start doing these things where you start putting signs. You say, well, I want sort of not sums, but differences of things like that. And there, there's a huge industry in this Q-series world where I mentioned that after Ramanujan, there are a lot of people who came up with examples of mock modular forms. That's one of the examples. That's one of sort of a set of examples of mock modular forms. This example in AGS 5 that I showed you earlier, I mean, in physics, this is how, at least in the string theory counting problem, you always have some partition type problem. This one turns out to be, well, I can tell you the technical details. It's interesting. Instead of 1 over 1 minus q to the n, you have 1 over 1 minus q to the n to the power n in product over n. So it's more like the McMahon function. Okay. So you can imagine, so this is related to not partitions, but plane partitions. Okay, so you can imagine that does not have modular behavior, but it seems to have some interesting behavior which has not yet been made very precise. No, so the answer is I don't know why, but in each case, it's certainly the question that you ask should be asked, and it always leads to some interesting answers.
That's good. Oh, I forgot to say, well, that was a really beautiful talk. I really enjoyed it. Thank you.